The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our next speaker will be James Shillstone. James is otherwise known as Jay. He's a third-generation Shillstone. To be involved in quality control of concrete for architectural products. He's currently involved with worldwide projects worth over $4 billion. He's a member of ACI 303, Architectural Concrete, and he's on multiple ACI, National Ready Mix, ASTM, and Transportation Research Board committees. With that, I'd like to bring Jay up and speak.
Good morning, or howdy. I'd like to thank, on behalf of the Northeast Texas chapter, I'd like to thank everybody for attending. Okay, now then, how many of you have seen something like this? Okay, and now this is an old one, I admit, yes. But you may have noticed, or may not have noticed, there in the middle of the screen, we have something that says probe and 0%. Now, I assume that since you're in this session, you know what that means. That means that there is supposed to be a moisture probe somewhere in the batching system, and somebody has turned it off. And so that's a problem. We're not getting any kind of measurements of the moisture of the sand as we're going through our production process. We want to have a moisture probe embedded or attached somewhere to the batching system to monitor the surface moisture of the sand, and preferably of the coarse aggregate if we can, as the material is being batched. But all too often, these probes are being turned off because there is widespread belief these things are not accurate. And sometimes they're not accurate if they're not properly installed, not properly calibrated, and so on. But today's moisture probes are much more accurate. We have more things that are going to help us get an entire moisture system. Now, what is this bit about moisture? Again, I assume you know we're going to be going back and looking at stuff that you might already know. If we take a load of sand and we oven dry it and we knock out all the moisture, there is no water in that sand. If we add a little bit of moisture, that sand is going to absorb that like a sponge, and we're not going to have any moisture on the surface of the sand. When we get the right amount of moisture, we're going to fill up that sand particle or rock particle so that we have no moisture on the surface, and we have all the absorption accounted for in that particle. And that's, at this point, if we get more moisture, no more moisture can go into the sand or stone particle, so we wind up having moisture on the surface, adsorbed onto the surface of that particle. Now, it's this moisture that's on the surface of the particle that we're concerned with, because that moisture is going to contribute to changes in slump, changes in water-cement ratio. It's going to affect the strength of the concrete. And so we want to be able to determine how much moisture is on the surface of that particle. And we can do that by various methods. We can take a sample of aggregate, we could put it in an oven and dry it out, and then subtract out the absorption to find out what the surface moisture is. We have a variety of, today we have a variety of moisture probes that you could actually stick a probe into the sand stockpile or the coarse aggregate stockpile. It's not so easy to do, but you can measure the moisture content using a probe stuck into the aggregate stockpile. But the typical method that's done in the concrete plant is to go out, take a scoop of sand, put it in a little pan, take it to a hot plate, cook all the moisture out of the sand sample, and then subtract out the absorption, and voila, we have a value for the surface moisture of the sand. And the trouble is, that is a little bit time consuming. You can do maybe a couple of those an hour if you want to do all the calculations, because after you've cooked up the sand, you actually have to let it cool down a little bit before you measure the weight, because the temperature and the heat variations can actually cause the scale to fluctuate somewhat. So you want to let the sand cool down before you do the weight. Also, you don't want to burn your hands or mess up your scale if you've got a plastic pan for your scale. So anyway, we're very concerned with determining the surface moisture content. And that's where moisture probes can come in. So why use moisture probes? Let's say, for example, we have a concrete mix that has 1,300 pounds of sand. Now, if that 1,300 pounds of sand has 6% moisture, that means that if we truly want to batch 1,300 pounds of sand, we have to multiply 1,300 times 1.06 to get 1,378 pounds of sand. And when we do that, we're going to get 1,300 pounds of sand and 78 pounds of water. We have to deduct that 78 pounds of water from our mixing water, because if we don't, we're going to increase our slump by about 8 inches. And we're going to increase our water-cement ratio by about 0.15. So this is important. This is not just small figures. This is important to be able to adequately determine what the surface moisture is. If we have 3% moisture, we want to change our adjustment in our sand content. If we have 9% moisture, we're going to have water running out of the sand probably, and we need to be able to make an adjustment for that. So it's very important to be able to determine what the moisture content is of the sand, and preferably of the coarse aggregate too, if we can, because it's going to affect the slump, it's going to affect the water-cement ratio, it's going to affect the strength. Now, at this point, I assume you all know this, because that's why you're in here. You're concerned about slump variations, you're concerned about strength variations, and you recognize that water is the culprit, and that being able to accurately measure the water in the aggregate at the plant is also very important. It was part of one of the sections of water supply that Eric was talking about. Now, let's get to the different types of moisture probes that are available. Traditionally, we had an electrical moisture probe or a resistance moisture probe where you actually passed electric current through the sand. The more moisture you had, then the more current you were going to be able to pass through the sand, so the higher your reading. But these things were notoriously unreliable, whether it be through setup, through calibration, or what have you. And so the next type that came out was the microwave. And this is the type that you're probably going to see most often today. The majority of the probes that I was able to find online when I was doing a search wind up being the microwave type. And then there are also nuclear probes as well. But the majority of the ones that are currently available that I'm aware of are microwave. But the other part about the probes that you have to understand is they're part of a system. Now, back when we had the electrical resistance, this was an analog device. You measured the current, and you had a meter that was showing you what the moisture content was. It was a continuous reading. It was going up and down. But as we're doing the microwave type probes, we're getting digital readouts, and so we're going to be getting multiple readings every second. And then those readings go into our batching system. It doesn't do us any good to be able to measure the moisture if we can't make adjustments in our batch weights of materials. So we're going to be taking the information from the moisture probe, doing multiple readings, feeding it back into our batching system, and then we have to be able to make adjustments in the batch weights to make sure that we're getting a consistent water content. We don't want to just have one reading at the beginning of the day and run with it all day long. That doesn't usually work, especially if you have a rainy period or as you're getting multiple deliveries of aggregate. So the moisture probe is only part of a system. You have to look at the whole system, how it ties in with the batching equipment as well, to make sure that you're getting the proper adjustment from the moisture probe so that you can get more uniform moisture. Now, why are moisture probes often not used? Because the slumps are still variable. One of the reasons that people have rejected the use of moisture probes in the past is they've tried using the moisture probe, they plug the information into their batching system, the batching system corrects the weights of the materials, and yet they're still getting slumps going up and down, and they don't understand why. They say the moisture probe doesn't work. Well, that may not necessarily be the case. There are lots of reasons, as Dr. Hover pointed out, why we have slump variations. We do have changes in water content, either from the aggregate moisture, from the wash water that was used either when the truck was washed down before the concrete was batched or when the truck is washed down after the concrete is batched. And also, a dirty little secret in the concrete industry is the batch man can actually adjust the amount of water that he's batching intentionally. If they want the concrete to leave the plant at a 4-inch slump, then he can hold back a little bit of water until he is sure that the concrete is at a 4-inch slump. If he needs to add a little bit more, he can. So we're talking about the use of trim water here. So actually the batch man can be making adjustments in the amount of water that's being batched manually. And of course, hopefully all this is being accurately measured in the batching system so that when you get your batch weights on your batch ticket or you go back and look later, you can actually find out how much water was placed in that truck. Now, the other dirty little secret is sometimes there's water supplies available at the batch plant that don't go through the normal metering system. And so water can be added without showing up in the metering system. But that's why you do batch plant inspections in advance, to make sure that you understand how the water is getting into the batch system and to make sure that you're not going to have unmeasured water going into the batch system. Secondly, as Dr. Hover pointed out rightly, we have changes in air content. After our air content goes up over about 3%, we actually are going to get, we can get increases in slump as our air content goes up. So I can take two concrete batches with exactly the same amount of water. If one has about 6% air and the other has about 3% air, the one with 6% air may have 2 to 3 inches more of slump than the one with 3% air. So variations in the air content can affect the slump. And in fact, you can use things like Excel or other software products to be able to accurately develop relationships using something called multiple regression analysis, which use water and air content as a predictor of slump. And you can develop equations for this. So if you want to be able to set up those relationships in advance, you can. But that's typically going to vary from material to material and maybe even from plant to plant. So you want to be able to look and see how you can do this for a specific set of materials. Changes in temperature. Hot weather will typically give us lower slumps for a given water content. Changes in particle grading and texture. If our sand becomes finer, it takes more water to coat the surface, so we may have the same amount of water, but all of a sudden we have less slump because we have finer sand. We're having to coat the surface. A rougher particle shape is going to require more water to get a certain slump. So again, we have changes due to particle shape and texture. And the moisture meters, of course, may not be accurately set up. There has to be a calibration done between the moisture meter and the materials to make sure that you are getting accurate readings. So there are a lot of reasons that we can be getting variations in slump with regard to what the moisture meter says. And we can't just throw out the baby with the bathwater. If we have variations in slump, when we have what's supposedly a good moisture meter system, we need to look at the other reasons that the slump can be varying and determine if they are causing problems. Oh, and of course we can't ignore the moisture in the coarse aggregate. When we're batching 1,800 pounds of stone, then even a 1% moisture in the coarse aggregate is going to be 18 pounds of water. That's 2 inches of slump. So you need to be aware of what the coarse aggregate moisture content is, especially when the aggregate producers love to wash down the material just before it leaves the plant so that they're not only selling coarse aggregate, they're selling water as well because they're getting paid by the ton. So coarse aggregate variations can be very important in determining what the true water content is. Other factors affecting moisture meters, the materials variations in aggregate source, including absorption and grading, you actually need to calibrate moisture meters for each different aggregate source. Because if what we're measuring with the moisture meters is the total moisture and not just the surface moisture, and then we deduct out the absorbed water. So if we've got two different aggregate sources that have differences in absorption, we're going to need to be able to have different calibration curves for those. So it's important to get the right calibration for each of our aggregate sources. Excessive moisture, whether it's from water dripping down from excessively wet aggregates, whether it be steam in a bin for the northern climates, excessive moisture can also throw off these moisture meters. So we want to be aware of how the excessive moisture and how moisture dripping down on the sides of the bin on the inside is going to affect the readings from the moisture meter. And finally, we have our good old friend FILO here. FILO stands for first in, last out. You may not be aware of it, but when you've got an aggregate bin here, and you fill it up, what you're actually getting coming out through the discharge gate right down here is the aggregate on the top of the bin. If it's like when you're in a bathtub and you open the drain and the water starts tornadoing out down into the drain, well, the same thing happens. The sand starts coming down here. If you let your bin get partly empty and then fill it up again, you're not actually batching out the sand that you put in first. You're batching out the sand that you put in last because it's coming down the funnel right through here, and that's what's being batched out. The better way to charge your hoppers is to go ahead and let the aggregate get all the way down and not just fill it up on a continuous basis. Let the aggregate go almost all the way down and then refill it so that you're working with continuous material. Otherwise, as you let the aggregate content go down, you'll start getting into previous layers of aggregate, and those may have substantially different moisture contents. So in one batch of concrete, you may have 3 or 4 different sources of sand, and you're going to have 3 or 4 different moisture contents. Looking at material stockpiling. What happens all too often is we've got a bin right here, or a bin set out on the ground. We add our first load of sand, then we add another load of sand in front of that, and more loads of sand. Well, the sand that usually comes in is going to be the wettest. So here we have had sand that's had time to dry out. And so what's happening is our front end loader comes here, grabs sand, gradually works its way back, is getting into drier and drier material, which is going to impact the moisture content in the sand. And then all of a sudden, we're working in this material, we get another load of sand dumped in front of it, and it's totally soaked, and water's dripping out of it. So we've got a tremendous change in our water content. The best thing to do is to have a system like this, where you can have the trucks come in, dump the first load right here, and then start dumping successive loads, and the front end loader can come here and start taking the drier material first. By the time they get back here, then this material has had a chance to dry out, and so we wind up getting more consistent sand. The only trouble is I very rarely find a batch plant that has enough room to be able to do this type of arrangement right here. And so most people go back to this type of arrangement because of the space-saving ability, but they tend to ignore the fact that just because this is more convenient, they still have this same problem. They're getting one load of sand that's wet, then another load that's dry, and then another load that's wet, and those are going to play havoc with and maybe even sand from different sources, which is going to play havoc with your calibration of your sands and your moisture meter. So, factors that affect the moisture meters in the plant, the location of the probe placement. You don't want the probe to be high up on the side of the bin. You want to be have the probe located right at the discharge gate where the aggregate is flowing over it. The bin size and shape, whether it's trapping material or whether it's adequately draining the material, is going to have an impact. The timing of the readings. Like I said, we have digital readings, so we're getting periodic readings. If we're getting one reading every minute, that's going to give us potentially a different result than if we have 30 readings every minute. The timing of the adjustment. Some moisture systems will take a reading at the very beginning, set the batch weights, and then they will batch those weights even though the moisture of the sand that's passing over the probe may vary over time. Other systems will take continuous readings of the batching system as the material is going over the probe, make adjustments so that it's continually updating the amount of aggregate that's being batched. And then, of course, we're also interested in durability and maintenance, ease of replacement of the probes itself, because if we have a worn-out probe, we're going to be getting different kinds of readings than we would for a well-maintained probe. So what to look for in a moisture system? You're looking for accuracy, which typically translates to ease of calibration, the ability to have multiple profiles for multiple materials. Continuous measurement. You want to have multiple readings every minute to be able to make adjustments. You also want to have something that is easily maintained. Now, I will say, in the basis of full disclosure, I work for Command Alcon now. We have our own moisture systems, but these things apply to everybody that makes moisture systems. Whether it's Hydronics or any other company that makes a moisture probe, it has to integrate with the system to make sure that we have a system that's going to be able to do these things. And so you need to look at the systems, understand the drawbacks and the benefits of each different type of system to be able to fully understand what's going on. Also, you need to see what's happening in the concrete batch plant to make sure that you understand how the operations of the batch plant, how the storage of the materials, how the charging of the hoppers is going to affect the variability of the concrete batch, of the concrete that's being batched, and the total moisture that is the total water content that's being batched. And proper design and installation, the proper placement of the moisture probes, making sure that everything is set so that there are cases that I've seen where the moisture probe all of a sudden comes out and it winds up in the load of concrete. So you need to make sure that everything is properly installed, properly maintained, and so to ensure that you're getting proper readings all through the entire production process. And you also want to have a user-friendly interface, something that allows you to determine changes in your materials, so that we're not just having a batching system where somebody has decided this moisture probe's too much trouble, they turn off the moisture probe, and then you have no adjustment whatsoever. So I'd like to thank you all very much for your attention.
Hi, Jay. I'd like to ask about the difference between moisture probes for sand and for coarse aggregates. Can you talk about that a little bit?
I'll be honest, I have almost no experience with moisture probes use in coarse aggregates. I may defer that question to Karthik. Do you have any comments on that, Karthik?
I think there are some that are good that people have used for coarse aggregates. Do you say?
No, we don't.
Our system can supposedly work with coarse aggregate, but I don't know anybody that has it set up with a coarse aggregate right now, so I better defer on that one.
Earlier in your discussion, when you were talking about the importance of this, you were looking at moisture contents and aggregate weights. When you showed your discussion, I think it started with 1,300 pounds of sand.
Right.
Very important principle. One of the things I keep running into around the country is not all that uncommon for ready-mix producers to define moisture content on the basis of the SSD weight of the material, where a 0%, a zero moisture sand would be a sand at SSD, which means then a zero free water. So that definition is frequently used. We take a look at ASTM, the definition of moisture content is based, zero means oven dry. Now for coarse aggregate, that difference is really very small. But if you have a sand with a high moisture content, that difference in definition can be significant, especially if it's really very wet. So you can have the technician for the concrete plant who's calibrating a meter using one definition. A testing technician comes in from a test lab who is used to using the ASTM definition. They can be operating on two separate definitions of the term moisture content and not realize that if the one guy says 3%, the other guy says 3%, those are entirely different 3%.
Right, that's a very good point. In fact, I'm missing the ACI 211 meeting, mixture proportioning right now. We spent a whole meeting one time discussing that very thing. If you've got lower moisture contents, 3 or 4%, then you're only talking per cubic yard, maybe a pound difference or so. But once you start talking 8 or 9%, especially with materials with high absorptions, then it's the high absorption that is really going to get you on the difference of that. Then you can start talking 5 pounds or more, which can dramatically affect your water cement ratio or your slump. It's a very good point, Ken. I sort of simplified over that one. Any other questions? All right, well, thank you very much then.